Aqui é a primeira aula desse curso com o título que eu vou botar em inglês aqui. Eu tenho umas notas de aula aqui, eu vou procurar fazer notas para cada aula para vocês terem algum material para acompanhar. As notas vão ser bem básicas, várias coisas vão ter referência para artigos ou livros onde elas estão melhor provadas, né? Bom, o nome do curso é esse aqui, caso vocês não lembrem. E o objetivo, então, é fazer uma introdução bem introdutória, se é que se pode dizer isso. Do you speak Portuguese? So, would you rather have me switch to English? Because... Well, I mean, no, I mean, the rule is if there's one person in the room who prefers English, then we switch to English. Okay, so from now on, these lectures will be in English. And as I said, there'll be lecture notes at the xerox outside that you can take a look at after class. Yeah.
And the goal of these lectures is just to give you some very basic and very rough introduction to things related to these three words. I mean, the main goal is really to prepare you for the workshop next week. But not everything that I'm going to talk about here will be featured next week, nor will everything that will be featured next week be covered by this class. And, well, I've got some references here, but I guess I'm not going to write them down, and you can take a look at them later when you photocopy these. Right? So let me just say what the main objects of study will be. Well, I introduce well, there will be essentially two kinds of random matrices here that we'll be studying. Some of you might have heard this phrase random matrix before. And it's, of course, random matrices are, of course, a very important part of modern day probability. There are books written about them. There are many papers, many important works by several prominent researchers. And here we're going to be talking about very specific questions about random matrices, which are perhaps not the ones that you're most likely to see in a pure probability conference, which nevertheless are related to those questions, but somehow of a different nature. So the first kind of random matrix that I'm going to be talking about here, what I'm going to call Wigner or Wigner style random matrices. And I mean, the idea is I'm going to introduce these, and I'm going to give some potential application of the things we're going to do later. And then I'm going to introduce another class of random matrices and give potential applications of them as well. Right? So what's a Wigner-style random matrix? Well, let me sort of write it on the board instead of give a very formal definition. Well, it's a random matrix, so the matrix better be random. Well, which way is it random? Well, what we want is, first of all, we want a symmetric matrix. So we know that whatever we write over here, we've got to replicate over here as well, right? So x to 1 should be equal to this one. X to 2. And, well, if you have x3, 1, it should be equal to x1, 3. This. You have x3n, xn1, xnn. But given that we want a symmetric matrix, you want a matrix whose entries are almost as independent as possible in some sense. What I mean by this is that I want the random variables xij, where I just consider I less than or equal to j. I want them to be independent and have mean 0. Or, okay, without a comma here. And then I just define xji to be equal to xij if j is larger than I. So I mean, this is what ensures that I have a symmetric matrix. So I'm saying essentially is that, well, if you look at the diagonal and everything to the right of it, then these entries here are independent, and then I do whatever I need to do to get this to be a symmetric matrix, right? So these matrices were introduced by Wigner in a paper, a 1955 paper in the Annals of Mathematics. And the, well, his original model had all the xij's to be normal random variables with mean 0 and variance 1. And I mean, there are some particular reasons for why that's a especially nice case, as we're going to see later. He had a motivation in mind, which was to describe the spectrum of heavy atoms. I mean, if you look at nuclei of such atoms, somehow the spectrum of this matrix has to do with the spectrum of a very disordered atom, in some sense. And that's a more kind of phenomenological observation than actual mathematical theorem that you prove from first principles of quantum mechanics, say. But nevertheless, the model was important for him and became a very popular model. And these days, within mathematics, this is a huge topic of study. It's studying these matrices and other matrices you have with independent entries. Well, usually people look at the IID case, but you can look in any case. And for us, it would actually be important to consider no IID cases. So, well, as I said, Wigner had a physics motivation in mind. Let me give you a different motivation to study this kind of matrix here, which comes from, well, in some sense from statistics, which is this stochastic block model. And let me add here with two communities. So this is an example of a problem that somehow involves a matrix like the Wn over there. Right, so what is this? So, well, let's say you have numbers from 1 to n, so bracket n is just a set of numbers. And you partition the set into two parts. And I mean, so I want A and B to be non-empty and to have empty intersection. And for reasons that will become clear later, these are the communities. So you can think that these are just two different groups of people in some sense, right? Labeled by numbers from 1 to n. Now, for each two people, and again, I'm only considering I less than j, I have a random variable taking values in 0 and 1. And the rules are that these random variables are independent. But also that the probability that ij equals 1 is going to be different depending on whether I and j belong to the same community or not. Right? So the probability is going to be p if I, j both belong to A or both belong to B, which means they are in the same community. And the Q, which is typically assumed to be less than P, but if I and j are in A times B or B times A. So different community. And now what is the problem? I said it was a statistical problem, right? So the problem is you start out without knowing what A and B are, what the communities are. You're just given these random variables. And from these random variables, you want to find out A and B. Right? So the goal here is to infer this partition here from the random variables I, j. Right, so what does this mean? Well, let's take a closer look at what this model looks like. And just to see if you understand the problem. Well, let me first say how matrices come in. And maybe that'll also help us understand the model a little bit better. Let's say that I define, so okay, one approach to this problem is we set iji equal to iij if j is greater than I. And we set, well, we put indicators on the diagonal. They're 0. Why am I talking about diagonal? Okay, I want to look at this matrix here. Right? So I have an n by n matrix. I mean, you can think of this model in some sense in graph theoretic terms, right? So, and maybe I should be more clear about this. So you can, when this random variable I of ij equals 1, you say that I and j are connected, say they're friends, for instance. And if iij equals 0, it means they're not connected, they're not friends. And here, what I'm doing is essentially, I'm imposing that friendship is symmetric, right? So I'm saying if I is a friend of j, if and only if j is a friend of I. And nobody's friends with themselves. So, I mean, both of these assumptions can be wrong, right? I know people who are very good friends with themselves. It's very common to find friendship relationships that are not symmetric. But in any case, let's assume that for the time being, the model is idealized anyhow. And so you can build this matrix here. It's the adjacency matrix of this graph that I was discussing. Okay. Well, even if you don't know what an adjacency matrix is, it's just a matrix. Right? A 0-1 matrix. So now, remember that I told you that a Wigner matrix is a matrix where the entries are independent and have mean 0. This is not a Wigner matrix, right? Because these random variables here, well, on the diagonal, the means are 0 because they're always equal to 0. But outside of the diagonal, the means are either P or Q, depending on whether I and J belong to the same community or not. So you need to subtract something to make this equal to 0, right? So let's try to find a better way to write the mean of this random variable. Of course, this is only just the probability that it equals 1. And let me write it like this. So let's see if we all agree. So what we need to check here is that this tells us the same as before, right? Well, this is an indicator, right? So when you say indicator of set A at I, this is 1 if I belongs to A and 0 otherwise, right? That's just the usual indicator. So let's see. Well, if you take I and J that belong to the same community, then either you have I and J in the set A or I and J in the set B. In this case, the expectation is P, as it should be. And if I and j belong to different communities, then either I belongs to A and j belongs to B, or the other way around, and you get the value q as you should. So everything seems to be fine about this, right? So but there's something else that's sort of hiding in here, okay, so now we have a good Wigner matrix, which would be the matrix where xij equals iij minus the expectation. Right? This is now a valid Wigner matrix, if we take this. Right, but there must be a reason why I introduced this matrix. Remember that the goal is somehow to infer A and B from the matrix here, or from the values of the indicators. Okay. So what about this matrix tells us that we should be able to infer A and B from the matrix itself? Well, let's take a look at this. The first thing I want to do is to rewrite this, to write the expectation of the matrix Mn. So what is the expectation of a matrix? Well, there's sort of two ways to put it. One of them is to say, well, the space of all n times n matrices is a vector space. The space of symmetric matrices is a subspace. And whenever you have a vector space, at least a finite dimensional vector space, you can define expectations by some sort of limit of discrete things, of averages. Right? The less complicated way to put it is just to say, well, the expectation of a matrix is by definition the entry-wise expectation. Right? And you can take that to be a definition. It agrees with the previous thing I said. But let's see what this matrix looks like. Well, let me say something here, which I maybe should have said from the beginning. For me, we're going to use this. For me, it's important that we use this notation that we sometimes use in linear algebra, which is that you decide from the beginning whether vectors are going to be column vectors or row vectors, and everything sort of develops from there. So I want my vectors to be usually column vectors. And now I claim that this matrix here, you can write it just using this formula here. You can write it in the following form. So it's P, indicator of A, indicator of A transpose, and let me emphasize that this is a transpose, plus P, indicator of B, indicator of B transpose, plus Q, indicator of A, indicator of B transpose, plus Q, indicator of B, indicator of A transpose. And now I'm telling you this is true. What do we need to do to prove that this is actually true? Well, we just need to check things, right? Yeah, except that maybe I need to subtract something from the diagonal, as I just noticed, right? Because if I equals j, I want these entries to be 0. So I want to subtract p times the identity here. I should add this to my notes because I forgot. Right, so how do we know that this is true? Well, we need to check that the ijth entry of this matrix, which is just its expectation, equals the ijth entry of this matrix. Right? What is this matrix like? When you have, well, just to recap some very basic linear algebra, a matrix like this, right, when you take two column vectors, and you have a matrix like this, well, the entries of the matrix are just xi, yj, well, I and j going from 1 to n. This is exactly what the matrix looks like, right? So if you plug in I and j here, you're going to get p times indicator of A at I, indicator of A at j, and then p, indicator of B at I, indicator of B at j, And you can go on and just check that we have the same expression as here. But I mean, I'm sort of making it sound very simple. I want to make sure that you all understand what I'm doing here. I'm just saying that if you want to write this thing down in matrix form, you can use these vectors, these column vectors, and then transposes, which are row vectors, and write this in this compact way. And I mean, this requires some checking, but it's really not complicated. So is this clear, or should we try to see very directly? So if nobody says it's not clear, I assume it's clear and move on. It's not clear? Okay, good. And, well, right, so let's, so does this make sense to you? More or less? Well, okay, so maybe we need to go very quickly through the linear algebra, and then, can you all see between these two lines, or does this block anything? Well, maybe I should try to move the line a bit. Can you still see? Okay, good. Right, so, okay, a vector for me is just a column vector. So when I write y transpose, this is a row vector. When I write x transpose y, okay, so this is, okay, let me write it like this. When you take y transpose x, this is the product of a matrix with one row and n columns by another matrix that has n rows and one column. So that gives you a matrix with one row and one column, which is a number, right? We take that to be a scalar, and actually that number is just the usual inner product. When I write this, it's the product of a matrix that has n rows and one column by a matrix that has n columns and one row. Well, one row and n columns is the best way to put it. So this is going to be an n by n matrix. And how do you figure this matrix out? Well, you have the usual rule for the matrix product. So let me maybe move this a little bit down. You have the vector here, x1, xn. You have y1, yn. Well, of course, if you have larger matrices, then you have longer rows here, longer columns here. Well, how do you determine the product of two matrices? Well, if you want to know entry I and j, you take the entry, you take xi, yj, and then you get a xi, yj here. Right? So again, if you had a matrix with longer rows here, and another matrix with longer columns, then you had the inner products of the rows and columns figured out. But here the inner products are trivial because you just have scalars. Well, maybe just to make sure, I mean, I had to subtract this pi here because what does this have on the diagonal, right? If you have, say, what's the one entry of the matrix? Well, 1 either belongs to A or to B, and you're not going to get, so these terms are going to be 0, one of these is going to be 1, so you get P, but I want the mean on the diagonal to be 0, right? Because the random variables on the diagonal are always 0. So I need to subtract this multiple of the identity here. And here's another way to write this, which is perhaps clearer. Where's the eraser? So the way to write it, I mean, it's just, the reason why it's not good is going to become clear soon. Well, I mean, the reason why it's not perfect. Right. So let's assume that by some stroke of luck, we knew that, you know, the elements of A are just the first few numbers, and then you have the elements of B. So you have A and B here as well. What would this matrix look like? Well, we know it has zeros on the diagonal. Well, this is, again, the expectation of M sub n. You got zeros all the way on the diagonal. But outside of the zeros, what do you get? Well, here you always have P's, right? You're saying, well, same community means expectation equals P. And the same way here. And here you have Q's. So in block form, this matrix would look like this thing I'm about to write, except you subtract identity. So this thing is P, P, Q, Q. But of course, you don't know, I mean, we don't know that the elements of A are the first numbers, and then you have the elements of B, right? In general, A and B are permuted in an arbitrary way. So in some sense, what we want is to find the permutation that puts the matrix, the expected matrix, in block form like this. And the question is, can we do it from data? I mean, so let me just say this. First of all, it should be clear from this that if you can approximate this expectation, then you should be able to approximate A and B. Why? Because you know that you have this form, right? So if you want, you can say, you can compute the eigenvalues and eigenvector of this matrix exactly, and they're combinations of the indicators of A and B. So should we do this? Maybe, right? This is not in the notes, but we can do it quickly, I think. Well, from this, it's very simple, and I just need to remember. Right. So let me. Move the definition over here. Well, one thing you can note is that this expectation is, well, this matrix is a very large matrix, an n by n matrix, but it's actually a rank 2 matrix. Right? Is this clear? I mean, rank is just posto, right, in Portuguese. So it's just saying that it's, okay, well, this part here is a rank 2 matrix. But if you subtract this, then you get all the eigenvalues. So maybe I should start out by saying, well, when you have a matrix, and you add a multiple identity, you don't change the eigenvectors, and you just shift the spectrum, right? So if you want to know the eigenvalues of this, I can just add pi here. So let me, then you have this matrix here. Well, you don't exactly have this matrix because, as I said, the rows and columns are all permuted, but we know that doesn't change the spectrum either. I mean, so it's just a matter of seeing things in the right way. So let's see, okay, let me call this matrix A. No, not A, sorry. U. So what happens to U if I multiply it by this indicator vector of A? Well, it's, perhaps it's not the simplest thing to do in this current form, so let me write it in a slightly different way. So because in our current basis, A looks like this. It's a vector full of 1s up to a point, and then you have 0s. So this is a set A. So what do you get here? Okay, this is A, right? And this is A, this is B. So what you're going to get is a vector of p's in the set A, and then you have a vector of q's in the set B. Right? So if you don't remember your linear algebra classes very well, this is exactly the time to remember everything you've ever learned. But all I'm saying, well, how do you take the matrix product, right? You take this, well, you just look at the rows here. I think it should be fine. And, right, am I doing this right? Or am I forgetting something? No, I'm missing a constant here. I need to have the cardinality of A here. So maybe it's easier if I do just, what should I do? Yeah, that's right. Let me look at it like this. No, okay, this is fine. And what now? Okay, maybe you should say, why is this true, right? So if you, maybe it's easier if I just take one canonical basis vector here. So say a vector that has 0, 0, 0 up to the ith coordinate, and then 0, 0, 0, 0. And let's say that this is the ith coordinate and that I belongs to A. And then it's easier to see what's going on. Because in this case, well, what happens when you multiply a matrix by the one canonical basis vector? Then you get just the ith column, right? So the ith column looks exactly like P, 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 and then Q, 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 where this is A and this is B. And here I'm using the fact that I belongs to A. So if I take an element of B, I'm going to get reversed, right? I'm going to get Q and P. So, and this means that when I take U and multiply it by the indicator of A, then this is going to give me, well, indicator of A is a sum of vectors of this form, right? So sum over all I belonging to A, a vector of this form. So I'm going to get the size of A times the result I got for each vector, which is this P, 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 Q, 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 Q. And let me write this down in a more organized way. So I mean that U times the indicator of A equals kernel of A times P times indicator of A plus kernel of A times Q times the indicator of B. And you get almost the same thing for B in here. You get kernel of B times Q times indicator of A, kernel of B times Q, times P times indicator of B. And maybe this is going to take a bit longer than expected. And since this is not the main point anyhow, so what I want to say, I mean, what I want to get from all of this is just the following fact. I mean, here I'm assuming that everything's a nice block form, but even if it isn't, you can very easily check that the eigenvectors of this matrix U, which are the same as the expectation of Mn, they are combinations of the indicators of A and indicators of B. Essentially because when you take, if you try to find eigenvectors in the span of these two vectors, then you have just essentially a 2-by-2 problem, essentially. This act on these two vectors, the matrix U acts as a 2-by-2 matrix, right? It maps indicator of A to a combination of indicator of A with the indicator of B, and maps indicator of B to a combination of indicator of A and indicator of B. So it keeps the subspace invariant. So it means that you can diagonalize in this subspace, and it's not too complicated to check that because of this kind of calculation here, the span of U is contained in the linear combinations of A and B. That clear? I mean, it follows from this, right? Because for any canonical basis vector, what you get out of U is just a combination of indicator of A and indicator of B. So you have these combinations, and you can, it's not hard to write down the coefficients. It just takes a real while, and maybe it will detract from our main purpose here. So it means essentially this. So if we're given matrix U, or essentially if we're given the matrix expectation of Mn, we can infer the indicator of A and indicator of B, which are the things we want, right? The two sets. We can get that from the spectral decomposition of the matrix. But now comes the problem. That's the kind of problem we want to take a look at here, is remember that, I mean, this is all assuming that we know what the expectation is, and we don't know that in principle, right? And so let me just, let me just say that we need some sort of condition here if we need P to be different from Q. Otherwise, there's not even a rank 2 matrix, it's just a rank 1 matrix, and then you don't get much out. Right? We need something to distinguish between A and B, the two communities. Right, but here's the main question for us. Remember that you have this matrix Wn, which is Mn, and then you subtract the expectation. How large is the operator norm of Wn? And why do we care about this, right? Well, we care about this because if we know this norm is small in some sense, then we can hope that this matrix here, which is what we see in the data of the problem, is very close to the expectation. And we know that from the expectation, you can determine A and B. So maybe we can do some sort of approximation and determine A and B approximately from Mn, from the actual data, right? So the hope somehow, let me write it like this, is that this norm is typically much smaller than the norm of the expectation. And when I write this OP is just the operator norm here. So if I have a matrix, its operator norm is just, by definition, the maximum over vectors of norm 1 of norm of AV. And if the matrix is symmetric, it can actually do this. This is just the inner product, right, of V and A times V for symmetric here. I mean, what I'm saying here is not completely garbage, right? So there are theorems that tell you that if you have two matrices that are closed, an operator norm, and then their eigenvalues are closed, and under certain conditions, the eigenvectors are also closed. So for instance, you need certain conditions for that. I mean, I'm not going to specify what the conditions are, because if you have a matrix like the identity, where you have two, let's say the 2 by 2 identity matrix has two equal eigenvalues. So very close to the identity, you can get matrices that have any eigenvectors that you like, essentially. But once you have a non-degeneracy condition that ensures that the eigenvalues are somehow different from one another, then any matrix close by will have eigenvectors that are very similar to those of the original matrix. So what we'd like to say is that M sub n is a perturbation of this matrix. And using some sort of perturbation theory, we can hope that if this norm is small, then we can recover Mn, can recover the expectation from Mn. And later today, we're going to see that this actually makes sense. I mean, we're going to do a very simple example where you can very easily bound this norm. So it's essentially Wigner's original example that we're going to do. And then we're going to say a few words about what you can do in more general cases. Right, so this is the first class of random matrices that we want to consider. It's matrices with independent entries that have mean 0. And here's one application of these matrices that we're going to discuss. Actually, you hear a lot more about this on Friday's class, which will be taught by Afonso Bandeira from Princeton. So any questions about this? I mean, I'm sure it's easy to get lost in the notation and how we write things down. It's all pure linear algebra. So in some sense, even if something's not entirely clear here, I can assure you that you know all of this and that it's just a matter of going through the calculations. But the main idea, I hope, has been imprinted in your minds. I mean, we just want to say that the problem of knowing whether a Wigner-type matrix has small norm or not is closely related to several different problems, including this of finding communities in a network of friendships. And I mean, of course, there are variants of this problem where you have two communities or many different, more than two communities, right? Maybe infinitely many communities, and each individual is a point in some sort of metric space, and then you have a matrix that depends on distances. I mean, you can do all sorts of variants of this model, but this simple variant already captures some of the main ideas. So, okay, this is class number 1 of matrices you're going to consider. And now we're going to switch to class number 2. Maybe I'll erase everything here except for this matrix notation primer here. So the second class of matrices we're going to consider, I mean, the first thing that should be said about them is that they don't have independent entries, so they're a different class. And for much we're going to do, they don't even need to have mean 0. But, and the kind of motivation we're going to have for them is very different. And I guess the other thing I should say is that somehow the linear algebra is going to get messier now. So I'm going to try to go slowly, but if you find something difficult, please let me know. I mean, we need to make sure that everybody understands what I'm doing. Right, so this second class of matrices, I'm going to call them random covariance-type matrices. So let me write this name over here. And what we have is this. So we, well, in order to define such a matrix, we first need a bunch of random vectors. So I'm going to write these guys here. They're random, well, let's say they are IID, random vectors in RP. Well, P is just a dimension. And somehow statisticians like using the letter P for the dimension. I'm not entirely sure what the reason for that is. But, well, this is the dimension. So, and we're always going to assume they have finite second moments. So that, for instance, that norm of x1 squared is finite. Right, so what's the matrix? The matrix is this. I'm always going to call it by sigma hat n. It's just a sum. And now here come the transposes and everything again. So we need to make sure we understand what this means. Right, remember we have this thing here, right? Which, well, this was x, y prime. So let me give a name for the coordinates of the vectors, and because I already have subscripts here, I'm going to say that the coordinates of vector xi, I'm going to write them like this, with square brackets. Right? And so let's write down the terms of the sum. So what are the entries of this matrix here? Well, xi, xy transpose. So you're going to get if you take two numbers, L and R, you want to know what's the number of position LR of the matrix. This is going to be the lth coordinate of xi multiplied by the rth coordinate of xi. Another way to put it is just let's look at what this matrix does to vectors, right? So if you have sigma hat n acting on a vector v, this is going to be 1 n, sum of I equals 1 to n, xi transpose times v. And now a matrix product associative, right? So we can move these parentheses here. And now this is a scalar, right? This is the inner product. So this is just a sum, right? Where you have some coefficient here, but you have a sum of the vectors xi's, each one of the coefficient, that's the inner product of xi and v. And maybe let's write another formula here, which we're going to use later, just so we get a few more familiar with this. So what about if I do this? Right, so this is, you take this product, and you take the inner product with this, right? So you have V transpose, what we just wrote. Well, everything here is linear, so I'm just going to say this is a scalar. I can move outside. And I'm going to get V inner product with xi. And of course, these two are the same, right? They're just mirror images of symmetric images of one another. Right. So why do we care about these matrices? Well, I haven't said much about it yet. But well, let me just point out firstly that if we have something which we call the covariance matrix of a random vector. So if we have a random vector with mean 0, then this matrix here is just a covariance matrix of x1, which I'm going to call sigma. And the covariance is an important thing. For instance, if you're trying to do the central limit theorem for that sum of random vectors, you get this covariance matrix showing up in the limit, right? So it's important sometimes to know what a covariance matrix is. We're going to give other reasons why this sort of matrix is important. And let me just point out that, I'm going to use this notation even when x1 doesn't have mean 0. So I'm just going to say this matrix by definition is equal to this. And how do we define this? Well, it's just entry-wise expectation, as we said before. And right, so in general, we have that this matrix is an average of IID matrices with mean sigma. So the strong law of large numbers implies that the probability that sigma n hat converges to sigma as n goes to infinity is 1. What do I mean by this, right? There are many possible senses you can give to this thing here. One is just to say that if you look at any entry, well, you fix two numbers, say 1 and 7. Does entry 1, 7 of this matrix converge to entry 1, 7 of this matrix? The answer is yes. And that holds for 1, 7, 1, 1, 2, 3, 4, 11, or whichever two entries you prefer. Right? So now the space of matrices of n times, well, p by p matrices, right, which is where we are. So sometimes we write the space of a p by p matrices, we write it like this. The space of matrices is a finite dimensional vector space. And we know that on a finite dimensional vector space, any two norms are equivalent. So you can say that, for instance, you can rewrite this. I mean, I said, well, this matrix converges to this one entry-wise, but that's the same as saying that, well, the operator norm converges to 0. And any other norm you can put here will also work. Right, so what we expect typically is if we take a large n, is to see a sigma hat n that's close to sigma. And the main problem we're going to have here is to quantify this convergence. Meaning, if I want to, given a finite n, what's the probability that this norm is larger than epsilon, for standard epsilon, for instance? And how does it decay with n? Does it decay fast or slow, or what happens, right? And why do we care about this problem? Well, there are many reasons. One of them, as I said, is that covariance matrices are important in themselves. But let me give you another motivation, which comes from something very old and very important in practice, which is ordinary least squares. Okay, maybe we're gonna, yeah, I guess I could write things over there, but then I'm gonna need this very quickly, so, okay, I'm just gonna leave the definition here. And right, so what is least squares? Well, let me first start with a theoretical question, which is this. So suppose we're given a random variable, r, which is square integrable. We're given a vector x, a random vector that is. And I'm going to say it's also square integrable in the sense that the norm, the squared norm, has finite expectation. This is the same as saying that each of these coordinates is in L2. Okay? Just because this here is the sum of the squares of the coordinates. So now the question, the theoretical question, and what is the linear combination of the coordinates of x that gives the best approximation for y. Now there are many ways to to think about this question, well, I mean, they're all equivalent in the end, but let me say precisely, first let me say precisely what I mean by this. So what I really mean is that, so what I want is I want numbers B1, BP such that the expected value of y minus sum of y equals 1 to p beta I x I is minimal. And what I mean by minimal is minimal over all choices of these numbers, right? Which are just scalars. And now let's there's a vector way to write this. So you can write the vector here. This is the same way. You want a vector in RP, which is the vector of these coordinates, such that you have that the expectation of y minus x inner product beta min square is minimal. It's the same, right? Because this is just the inner product of x with beta. So what you get is a sum like this. Each coordinate of beta multiplied by each coordinate of x. So here I've been writing that I want the guy that achieves the minimum. Why is it clear that the minimum exists? So Lucas said, or made kind of this motion with his finger, and not entirely sure what he meant. Does anybody want to try another sort of gesture that would perhaps be clearer? Yeah, it's a projection, right? So it's, if you really want to do it kind of in the functional analysis way, we have that, well, y belongs to L2 of your probability space. You have a subspace here, which is spanned by these guys. It's a finite dimensional subspace, so it's closed. And it's a closed linear subspace. And then, this implies that there exists a unique linear operator from L2 to the subspace, which is the orthogonal projection. And what it does, it takes any random variable z to a pi projection of z, and you can characterize this projection in many different ways, right? One of them, you can say that 1 z minus pi vector z, if you take the L2 norm, this is the infimum over u belonging to the subspace of norm of z minus u, L2. There's another way, which is just to say that z minus the projection is orthogonal to the subspace. These are actually equivalent here. Right, so this is sort of the Hilbert space way to prove that there is a minimal projection. I mean, there's something missing, right? Which I didn't say anything about the linear operator here. But of course, I mean, whatever, since we know that pi x of y belongs to the subspace X, this means that pi x of y equals a linear combination of the coordinates of X. Well, maybe you can say it both ways, right? If you have something that's a linear combination, it's the projection of somebody. And if you have somebody who is a projection, it's a linear combination. So this implies existence, it implies uniqueness in the sense that if you have two vectors beta that give you the minimum here, it means that they correspond to the same element of L2. You have two linear combinations of the x's that give you the same random variable. But here's what I want to get out of this discussion, which, and this is going to be important for us later. And it's just a simple proposition or lemma, whatever. I think I wrote it as a fact in the notes, but we're going to prove the fact. So take beta min belonging to RP, and well, let's define a function L of B, which is just the expectation of y minus x squared of B. This is going to call sometimes a loss function. It tells you how bad a vector beta is in terms of approximating y. And so let's say this, that beta min is a minimizer of the loss function if and only if the random variable epsilon that you define is like this satisfies the expectation of epsilon times x equals 0. And I have to be clear about what this means. Here we have a random vector. Here we have a scalar. So when you multiply a random scalar by a random vector, you get another random vector. And you can ask what the mean of a random vector is, right? If it's, and I'm saying that if this is 0, it's because beta min minimizes a loss, and vice versa. I mean, this is essentially a version of this thing here. That if you take y, subtract the projection, this is orthogonal to space F. Well, let me anyway prove why this is true. Right? Actually, I'm going to prove just one direction. The other direction just means you reverse the calculation. And let me be clear that the main reason why I'm going to prove this is true is because of the linear algebra that gets involved here. Just to make sure we all understand what's going on. Right, so what's the proof of the proposition? Yeah, let me put it over here. So as I said, I'm just going to prove one direction. And that if we know that you minimize, right? So this is the direction I'm going to prove. So if you take any vector in RP and you take any t, any scalar, say, greater than 0, we must have that L beta min plus t times v is greater than L of beta min, right? Because this is a minimizer. So because the right-hand side is minimal. I mean minimal, it's minimal over all possible vectors that you might stick in here. So now let's write this, right? So the way we define things, this thing here is precisely the expectation of epsilon squared. Why is that? Because, right, well, what's the loss function? It's the expectation of this thing. If you take beta equals beta min, what you have here is the expectation of epsilon. Right, so Right, so let's write now L of beta min plus TV. This is the expectation of y minus x times beta min plus TV squared. Now for simplicity here, I'm going to note that y minus x transpose beta min is just epsilon, the epsilon we just defined. Right? So we're going to get epsilon minus x, well, t times x inner product v squared. Can everybody see why this is true? I mean, it's sort of, the notation can be a bit confusing, right? But this thing here is just y minus x transpose beta min minus x transpose t times v. And this is the epsilon. So epsilon minus this, and the scalar moves outside. So this is what I have here. So now I have, well, just I'm going to expand the square here. Is this okay? Just expanded the square. I mean, here I'm using implicitly all the time the fact that y is square integrable, that x is square integrable, so all the expectations are well defined here. If you want, you can check this. Right, and as we said, all of this is greater than the expectation of epsilon squared, which is just this thing here. Right, so you can, so the main consequence we get out of this is we can move things, so we can move this to the other side. Well, these two are going to cancel. We get this. 2 times t times expectation of epsilon x v is less than t squared expectation of x v squared. Well, since t is greater than 0, I can divide by t on both sides. And then I can send t to 0. Right? So I'm sort of differentiating this expression with respect to t, essentially. And what I get from when t goes to 0 is that this expectation here is 0 for any v. But let me be clear about what I mean here, because now there's going to be a kind of a jump. In the notes, I sort of wrote this differently, but I want to do it kind of the nicer way here. The nicer way is complicated at first, but it's going to help us out later. And right, so what does this look like? So you have the expectation of epsilon x where v is less than 0 for all v in RP, right? So this is what we just showed. But notice that if I replace v by minus v, I proved that this expectation is larger than or equal to 0. So what I actually proved is that this is equal to 0 always. Right? So what I claim now is that I have this thing here. That this is, well, no matter what's inside, this is equal to this. So here I have an expectation of an inner product, right? And I'm saying that I can have So it's the expectation of the inner product of a random vector with a deterministic vector. And what I'm saying is that I can move the expectation inside the inner product, so to speak. So why is this true, right? So suppose you have anything of this form, any random vector of this form, right, where Z belongs to Rp and is random. So this thing here, by definition, is just this sum here, right? Which is just this sum here. And this, look, you have this, the vector whose entries are these values is just the expectation of the vector Z. So this is just the inner product of Z with V. Right? The notation is a bit confusing at first. We should all get used to it. So, and why is this important? Well, there are many other ways to make this last step, but the way you want to do it here, I'm saying I have this vector, which is just an expectation, and we know that this vector has inner product 0 with everybody. Right? What does it mean? It means that, so okay, this is sort of an aside, and this saying that, well, so this vector here must be 0. Well, another way to do it is just to say, well, take V to be the ith canonical basis vector. So here you're going to get epsilon times xi, the ith entry of x. And you're going to see this expectation is 0. And then you can use this information to show that the expectation of this vector is 0 as well. So that's how I wrote it in the notes. Okay? Right, so this proves half of that statement we had here, which is that saying if you have a minimal vector, it's because this guy, this epsilon, satisfies this equation, which means essentially that epsilon is orthogonal to the coordinates of x. That's all this is saying. Orthogonal in level 2. Right? And it's very easy to go the other way, so I'm not going to do it. Essentially, you can, if you do everything backwards, you get back to this equation here for all v, for any v. Essentially. You don't even, well, you can get the t anyway. Right, so, but of course, I mean, this matrix here hasn't appeared yet, right? So I'm doing what I said. I had a very clean theoretical problem, which is I give you a vector x, a random vector, and I have a random variable y, and I want to know what's the best linear combination of the coordinates of x in order to approximate y in this L2 sense. So that's a very clean theoretical problem, except that in practice you can never solve it, right? Because you don't know the distribution of x or y. So in the way people use this least squares method, I mean, this sort of problem comes up in practice precisely when you don't know what the relationship of x to y is. If you know the distribution of x and y, then of course you know everything you need to know. So in practice, you don't want to assume that you know the distributions and you can do these L2 calculations. So what is the practical method to do least squares? So let me write down what so in theory, you have x, y, rp times r, and then you have the data, which is what you have in practice. And the data is just IID copies of these guys. So just to make my notation simpler, I'm sort of assuming that all of these guys, x, y, x1, y1, x2, y2, x3, y3, up to xn, yn, are all defined in the same probability space, and they're all independent from one another. All pairs are independent from one another. Right? And somehow, what I want is I have this vector beta min. It might not be uniquely defined because, as I said, maybe, for instance, x has two coordinates that are equal, right? So then you can So x, say p equals 2, so you only have 2 dimensions, and the 2 coordinates of x are equal. So you have infinitely many choices. But in any case, in some sense, I want to find a vector from the data here, the IID data that I have. I want to find a vector beta that's essentially as good as the minimal vector. Right? So what is the goal now? Well, let me remember we had this loss function here. And you want to find a vector from the data. So it's a function of the data if you want. Such that this is as small as possible. So what is this? So this gives you how good the best linear combination is, right? The best linear combination of the coordinates of x. This is telling you, well, you found this vector from the data, and this quantity here tells you how worse the vector you found is from the best vector, how much it differs from the best vector. And we're going to write this down in a different form that says, in some sense, if this is small, this means that beta hat n is close to beta min. Okay? But let me just say, what's the method we're going to use to do this? So ordinary least squares consists exactly of taking the beta that minimizes this expression here. So what am I saying here? I replace the expectation here, which I don't know how to compute, by a kind of empirical expectation. So it's an average with respect to the data points. So if I fix beta and I compute this mean, I expect it to be very close to this, just because of the law of large numbers, right? For a fixed beta. The problem here is that my beta hat depends on the data, so I cannot apply this sort of law of large numbers arguments to just tell you how close these things are. Well, actually, I have even more, right? So I have the center limit theorem that tells you how the fluctuations are, assuming that this, for instance, has fourth moments. But I can't just say, well, this is close to this because nature's nice. Well, because this works for any fixed data. So if you fix the beta, and then I show you the data, then you know that this is close to this. But we're doing things the other way. We're determining a beta based on the data that we see. So in particular, if I take the sum here with beta hat inside, it's not an IID sum anymore, right? Well, the terms, they sort of look IID, but they all depend on this beta hat, which depends on the whole sequence of data. Right, so before we have a break, let me just consider this quantity here. I'm going to essentially redo the calculations that I did before. So, and here I want to have, so let me just write it like this. I want to know what the loss of beta hat n is. So I, of course, write this down as this, right? It's the loss of the minimal one plus this difference. And then I get here this difference without the t. Well, what you're going to get from this, we know already that this term is 0 here, right? we prove that this vector here is 0. We prove that you can even move this outside. And we know that this is going to be 0. Right? And there's no t now. So what we're going to get here is the expectation of x beta hat n minus beta min. And of course, this is the loss of beta min. What I'm saying then is this, that in order to know the difference between these two losses, you only need to know how this quantity behaves. Right? Is this clear? Now let's look at this expression here. Again, we have a calculation that's just like the one I'm about to raise, but, well, it's a bit different, but it's just... Well, recall we had this notation here for the expectation of this matrix, which was sigma. Now I'm going to write it with x instead of x1, because x1 and x have the same law, right? Okay. Now I have a quantity here, which is like the expectation of x in a product v squared, which is the same thing as this thing here. Do we all agree? It's again because all these matrix products here, they are associative, right? So this is a product of this scalar by this scalar, which is this. So what do I have here? I have, this is a matrix, right? It's a random matrix. So I have something like this. And what I want to do is I want to move these v's outside. Why can I do that? Well, let me do it just like what we did not too long ago. So I have a sum over I and j of vi, vj, mij. And then I can use linearity of expectation and move all these scalars out, all the fixed numbers outside. And now this is precisely v inner product with expectation of m, v. Right? But what's this m? M is this matrix here. So we know what this expectation is. This is just sigma. Right? And let me note that this matrix here, sigma, it's always positive semi-definite. You remember what positive semi-definite means? It just means that, well, this is always greater than or equal to 0. It's also a symmetric matrix, and that maybe is a little bit harder to see, but it comes from the fact that this is symmetric. Right? So when you have a matrix that's positive semi-definite and symmetric, it always has a square root. What you do is you diagonalize it, and you take the square root of the diagonal elements, of the eigenvalues, and that's the square root of the matrix. So you can write this as the norm of the sigma 1/2 v squared. Is this clear? Right. All I'm saying is that this expression here, if you want, is just the inner product of sigma 1/2 v, sigma 1/2 v. So I'm using the fact that you have, not only you have a square root, but it's a symmetric square root for sigma. Okay, so in fact what this expression here is just the norm of this symmetric square root applied to beta hat n minus beta min. So what's the conclusion here? The conclusion is that the loss of the OLS vector that you get from here minus the minimum loss, you can write it down as a norm. It's a distance between these two vectors, except that the norm you use is not necessarily the Euclidean norm. It's a norm, well, actually it might be a semi-norm in the sense that maybe this difference is non-zero and this norm is 0 if this matrix here, sigma, is rank deficient. But it's a kind of norm. It's a kind of measure of how far beta hat is from the true vector. Right? And when we come back from the break, we're going to see how, well, now when you try to analyze this method here, in some sense what you're going to get is instead of the sigma 1/2, you're going to get the sigma hat. And you get an inequality for that. Right? And yeah, so see you at 3:30.